I think there is a audio problem. I am not able to listen what you are saying. My email address, you can note it down. I think there is a audio problem.
They can send email directly here itself.
You can send email to this place. There is a audio problem. I am not able to listen what you are saying.
So they can send email directly here and we can clarify the doubts next class.
You can send email and you can get clarification in the next class. Hakim Engineering College. Savita, any questions? Savita Engineering College, any questions please? Very good morning to all of you. Actually, I welcome you all for the second session for discussion about design and analysis of algorithms. In the last class, we reviewed some of the fundamentals of algorithms. I told you already that algorithm is nothing but a set of instructions to carry out a particular task. An algorithm means it has got certain characteristics like input, output, finiteness, definiteness and effectiveness, and basically it is nothing but a blueprint of how to solve a problem. So, last class we had seen that two major components of algorithms are design and analysis. So, there are lots of design techniques that are available to uh, to guide us how to design an algorithm to solve a given problem, and also we had seen something about how to analyze the various algorithms. So, probably you can recollect, for our analysis purposes we classified our algorithms into two parts, two categories. One is called the iterative algorithms and second one is called recursive algorithms. So, already we have seen that in iterative version, actually we do not invoke any function calls to itself, but whereas in recursion programs we use the concept of work postponement. For example, 5 factorial means it is 5 into 4 factorial, like that it will go till the end, and once we know the final answer, the value will come back to the previous functions and then we will have the answers finally. So, I told you that with respect to the iterative algorithms, these are the things that are necessary, that is measuring the input size. We have to find the input uh, amount to the algorithm, because based on that only we are going to calculate the order of the algorithms, and then we are measuring the running time. And I told you that we are interested in finding the orders of growth. I gave you a layman example in the last class saying that it is nothing. If suppose if we want to buy an elephant along with goldfish, we can say the cost function is the cost of the elephant plus cost of the goldfish, and the cost of the goldfish is negligible. So, that means we are more worried about the cost of the elephant. So, this is what we are talking about, the orders of growth. And then I told you that we need to analyze the algorithm with respect to cases like worst case, best case and average case scenarios. So, probably you can recollect the example which we have seen in the last review. For this program segment, what we are trying to do is we are assigning the cost and then we are finding how many repetitions are going on, and based on that we are getting the cost function. So, in fact, we are extracting a polynomial out of this particular algorithm. That is why I said that these algorithms are called polynomial algorithms. And for discussing the rate of growth, we had discussed about the notations, and suppose can I say my program is having a complexity of order of n square, means I said we can use the concept of limits to find that. And suppose in this case if we have two things, f of n and g of n, and based on the rate of growth we can assign the asymptotic notation for that particular algorithms. Suppose if we have two functions f of n and g of n, we had already seen that if f of n is less than or equal to greater g of n, that is if the growth is less than, then we can say that we can assign a big O notation for that. Similarly, we can assign omega if the rate of growth is very high, and if it is almost similar, we have to assign theta. We had seen some couple of examples, n and n plus 1 by 2. If we assign the limit then you can see very well it is going to be a constant. So, that means you can see very well it is going to be theta. I told you that these algorithms need to be evaluated with respect to 3 cases: the best case, average case and worst case. Suppose if I execute my program, if I am able to get the results with the fewest number of instructions, then I can call that as the best case. And if I execute my program, and for that if I have to execute, if I have to have operations which are maximum, then in that case it is called worst case. Suppose if it is in between maximum and minimum, then I can call it as the average case. Out of all these 3 case scenarios, best case is the idealistic case. Say for example, if I want to search for an element, the element is available in the beginning of the array itself. So, that is the ideal case. Normally, in real world problems, idealistic scenario is very rare. So, best case analysis cannot provide much knowledge about how these things should be carried out. Worst case analysis provides the maximum information with regard to algorithm analysis. So, these algorithms convey the information about if this software is good today, then will it be good tomorrow also. So, that means it is better if we design algorithms taking the worst case scenario into our mind, so that the algorithm will be more optimal. Let us take a small example and then let us try to analyze these scenarios. So, let me take an example of a searching problem. So, the task is very simple. I have a big array that is full of data and I want to find a particular data in that particular array. So, this problem is called the searching problem, and there are different kinds of algorithm that are available for us. This algorithm is called linear search. So, that means here we are going to search for an item one by one till we are able to find the target value. So, this is the algorithm for sequential search. You can see very well the algorithm can be written in different manner. So, I told you last time that writing algorithm in a plain English may cause problems because natural language have lots of ambiguity. So, I said pseudocode is better because the combination of the natural language and the mathematics can convey the meaning in a better manner. So, you can see this algorithm is written like this. It is having certain name and you can see the steps. The steps of the linear search is like this. We are starting from the very beginning and I am searching for a key, and if key is not available, then we are going to the subsequent phase and then we keeps on checking for a particular key, and if key value is present, then we are returning the index of that particular value. Otherwise, if the end of the array is reached, then we are returning -1 as the indicator that the item is not present. So, this is the linear search thing. You can see very well you have an array. So, I want to find a particular value. So, you can take this particular array. So, here I am searching for an element minus 86. So, you can see very well how we are proceeding. So, we are starting from the first element of the array. I am comparing minus 86 with this particular element. If the elements, if the key is not matching with the value of the array, then we have to proceed to the next index. So, you can see very well how these things are going on. So, first comparison minus 23, I am searching for minus 86, 97, it is not what I want, 18, so 21, then minus 86 is what I am looking for, it is not the thing. So, now you can see. So, my key is now present in the 6th position of this particular array. So, I can proceed further. So, now you can see very well how this algorithm works. Suppose if I want to analyze this particular algorithm, then I have to see how many number of comparisons that is required to carry out this particular task. If I have to use the maximum number of comparisons, then that represents the worst case. If I am using only the minimum number of comparisons, then it represents the best case. And for a linear search, the best case analysis will be order of 1. Just imagine, I am searching for an element minus 86. Suppose if the array happens to have minus 86 in the beginning of the array itself, then using only one comparison I can find the results. So, the best case analysis of linear search is going to be order of 1. Fine. When the worst case will come, the worst case will come if what I am searching for happens to be the last element of the array, or if I am not able to find what I am searching for in that array, the worst case scenario will happen. So, the worst case scenario, I may require n comparisons to find out whether my element is the last element of the array or whether my element is available in that array or not. So, the worst case complexity of this algorithm is order of n. Fine. What about the average case? That means, let us forget about the ideal case where what I am searching for is available in the first element, available as a first element of the array. Let us forget about the worst case where my item is the last case. What is the average case? If you take the average case, fine, my key element may be the first element, may be the second element, may be the third element, and so on. So, that means any position of the array may contain my target value. In other words, the probability is going to be equally likely. So, that is the reason why for analyzing an algorithm with respect to the average case involves the concept of probability. So, in our case our target can be present anywhere in that array. So, that means it is going to be 1 by n. So, if you take the average case analysis of this algorithm, you can see very well the average number of comparisons is going to be 1 plus 2 plus 3 plus up to n and divided by n, and you know 1 plus 2 plus up to n is going to be n into n plus 1 by 2. So, now it is going to be 1 by n multiplied by n into n plus 1 by 2. So, n cancelled out. So, I am getting n plus 1 by 2. In the last session we had seen that what is important for us is the highest degree of the polynomial. Suppose if I have a polynomial something like n power 4 plus n power 3 plus something, what matters us is the highest degree of the polynomial. So, that means the algorithm is going to be big O of n power 4 only. Using the same idea, so this n plus 1 by 2 can be approximated to n by 2 and it can be approximated to order of n. So, that is the reason why we are saying that linear search algorithm, the best case is order of 1, worst case is order of n, and average case is also order of n. So, this information is quite useful to find the behavior of the algorithms. But the same thing, same kind of analysis, if I have to perform for recursive algorithms, things are becoming very difficult, because in iterative algorithms we are not calling the function by itself. So, that means I can easily assign cost to each and every statement. I can find the repetitive factor, based on that I can find the polynomial. But whereas in recursive programs this sort of analysis is bit complicated, because in recursion we are calling the function by itself. So, that means if I say I want to find 5 factorial, so it becomes 5 into 4 factorials. So, that means we do not know how many times functional calls will be made. So, last review I gave I gave an example of a Fibonacci series. If you try to draw the recursive tree, you can see very well it the tree is rapidly growing. So, because of these reasons analyzing the recursive program in a traditional manner is a very difficult task. So, that is why we are going for the concept of recurrence equations. So, recurrence equation is nothing but the discrete versions of the differential equations. So, here what we are trying to do is we are trying to analyze the sequence, and then we are trying to find the relationships among the data, and we are trying to capture that by means of a relationships. This is what we call as the recurrence relations. For example, you can take this particular example. Let us imagine I have written a program which generates a sequence like this: 3, 5, 7, 9, etc. So, if you carefully see, there is some sort of a relationship exists between all the things. That relationship is nothing but 2n plus 1. Similarly, if I say that you have another sequence which goes something like 3, 9, 27, 81 like that, you can see very well the governing relationship among the sequence is 3 power 1, 3 power 2, 3 power 3 and so on. So, that means you can see very well the relationship among the sequences is explicitly present. Sometimes this relationship need not have to be explicit also. So, sometimes we need to know the insight of the problem to get the recursive relation that exists among the sequences. So, let us take this particular example. Suppose if I have a sequence like 1 comma 1 comma 2 comma 3 comma 5 so on, immediately you can guess that this is nothing but a Fibonacci series, because the third term is nothing but your first term and second term. If you want to find the fifth term, it is nothing but your third term and the fourth term. That is, your f of n is equal to f of n minus 1 plus f of n minus 2, with the initial condition f1 equal to 1 and f2 equal to 1. So, this kind of relationship is what we are aiming at in analyzing the recursive algorithms. So, the procedure is like this. We have to find the kind of relationship that exists among the data that is generated by the programs. So, finding the recurrence equation is going to be the greatest challenge in analyzing the recursive algorithms. If the recursive relationship is known, then analyzing these algorithms is a cakewalk, but finding that is going to be a very difficult task. We will be discussing about this later on. Suppose if the recursive relations are known and the recurrence equation can be obtained from that, then we can solve that using various traditional methods. Certain traditional methods that are available for us are substitution method, then recurrence method, iteration method, and Master's theorem. Master's theorem is applicable only for a very small set of problems, and mostly Master's theorem is associated with certain problems which are solved using recursion and divide and conquer approach, and remaining problems can be solved using any one of these methods like substitution or recurrence or iteration. First, we will take up the case of the substitution method. Substitution method is of two types. One is called back substitution and another is called forward substitution. The backward substitution is called telescoping method. So, the procedure for applying this is like this. Number 1, we have to see the pattern and then we have to give a closed formula in terms of the initial conditions, and we have to plug values into the initial conditions to get the final formula. Let us take a example like this. Suppose if I want to find the closed solution for the equation a n equal to 2 into a n minus 1. In other words, it is something like I have written a program that involves recursion, and when I gone into the depth of the problem, I have understood that the recurrence equation of the problem is a n equal to 2 into a n minus 1 and the initial condition a naught is 3. If this is the case, in telescoping we can solve like this. We will go in the backward manner. So, a n equal to 2 into a n minus 1, again this becomes 2 power 2 a n minus 2. Now, you can see very well how it proceeds. This is equal to 2 power 3 a n minus 3. So, in this particular manner I can proceed. So, if I go on like this, you can see very well where this will end. This will end in 2 power n multiplied by A naught. A naught is equal to 3, that already we know, that is the initial conditions. Like the Fibonacci series, you have the initial conditions 1 and 1. Here the initial condition is given in the problem itself. So, now all you have to do is you have to really substitute this value into these particular equations. So, if you substitute A naught equal to 3, we will get a final answer, that is A n equal to 3 into 2 power n. So, this is the solution for this particular problem. So, what does this convey? This convey that the problem is involving certain complexity of computing a form something like 2 power n. So, that means there is a possibility that the problem may become very complicated. So, this is what I was telling you in the last review also, that there are certain categories of problems which we can call as the polynomial type algorithm, which are easily solvable, and there are certain problems which are non-polynomial type, in other words exponential type. So, I told you that one example of exponential algorithm may involve a complexity like 2 power n. The problem with this algorithm is that as n becomes more and more, the complexity of the algorithm grows in an exponential manner. This is the second method. This method is called the forward substitution. So, we will try to substitute the formula like we have done in the previous case, and then we will try to get the sequence, and by analyzing that particular sequence we will try to capture the behavior. For example, let us take the example of this particular problem. T n equal to T n minus 1 plus n. So, by removing n with n minus 1, this equation becomes T n minus 1 equal to T n minus 2 plus n minus 1. I am trying to replace n minus 1 by n minus 2. So, T n minus 2 is equal to T n minus 3 plus n minus 2. In this manner, if I proceed, I will have T2 equal to T1 plus 2 and T1 equal to 1. You can see how this proceeds. I am repeatedly substituting into the other equations. Finally, I am getting a sequence something like 1 plus 2 plus up to plus n. So, this is a sequence I am getting. So, this sequence is nothing but n into n plus 1 by 2. So, you can see very well this algorithm involves a computation of the order n into n plus 1 by 2. So, that means this is something like order of n square. So, I have given you one more example. You can see this particular example. So, for this algorithm, the recurrence equation is given as T n equal to T n minus 1 plus 2 by n, and a condition is given that n is greater than 1. Whenever we are putting a condition like this, the kind of asymptotic complexity we are getting is conditional. So, these conditions are necessary to carry out the analysis, and we are given a initial condition t equal to 0. So, whenever the equations are like this, we can easily solve by means of substitutions. Let us try to solve this using the substitution method. Tn is given. So, what I am trying to do now is that I am trying to remove n by n minus 1. So, if I do that, the equation becomes T n minus 1 is equal to T n minus 2 plus 2 by n minus 1. So, now I am trying to replace my n minus 1 by n minus 2. So, I am getting a new equations. So, proceeding in this particular manner, you can see very well it goes up to T 2 equal to T 1 plus 2 by 2. So, now we will try to add all the things. So, if you try to add everything, you can see very well we are getting a sequence something like 0 plus 2 by 2, it goes up to 2 by n. So, now if you try to simplify this by taking that 2 out, you can see very well this algorithm becomes something like logarithm of n. So, that means you can see very well this is approximately equal to 2 into logarithm of n. So, that means you can see very well this is the logarithmic type algorithms. So, in other words, for many algorithms which have a simple recurrence equations, we can go for either back substitution method or forward substitution method to find the answers. This is one method. The second method using which we can solve these equations are using the concept of the recurrence equation. So, that means we can solve this in this particular manner. So, again I am taking a small example to illustrate how these things are happening. So, T n equal to T n by 2 plus 1 for n is greater than 1, and a new condition is given, that is n should be the power of 2. Again you can see very well, you can find the sequence that are generated like this. I am substituting n equal to 2 into this particular equation. Suppose if I substitute, you can see very well it becomes T 2 equal to, see the equation, original equation is T n equal to T n by 2 plus 1. So, that means this becomes T 1 plus 1. T 1 is the initial condition that already we know, that is nothing but 1. So, 1 plus 1 equal to 2. We have already given the condition that n should be power of 2. So, that means the next thing should be T 4. So, you can find the answer is 3, T 8 is 4, T 16 5. So, now you can see very well the relationship goes something like this, T 2 equal to 2, T 4 equal to 3, T 8 equal to 4. So, now we can try to find the relationship that exists between n and the outcome. So, now you can see very well for 2 it is 2, for 4 it is 3, and for 8 it is going to be 4. So, that means you can see very well it appears that the kind of relationship that exists between this is T n equal to log n plus 1. Fine. How will you give a proof of this particular thing? In school mathematics, you know very well that suppose if a condition is true up to n, and if you could prove that for n plus 1 also, if this condition is applied and found to be right, then that constitute the proof of the whole thing. So, that means The induction hypothesis is, we have already found out that Tn equal to log n plus 1. So, n is power of 2. So, that means the induction step will be T of 2n. So, this is what we want to prove. This is what we are trying to prove, so that our initial assumption is right. So, T of 2n equal to log of 2n plus 1. So, let us try to prove this. So, our original condition is known. So, that means T of 2n equal to T of 2n by 2 plus 1. So, this becomes Tn plus 1, and already we know Tn is nothing but log n plus 1. So, you can see very well this becomes log n plus 1 plus 1, and 1 I can write as log 2 base 2. So, I can transform this to log n plus log 2 plus 1, and using the logarithmic thing, this becomes log 2n plus 1. So, now you can see very well how these things are accomplished. So, in short, I can summarize things like this. If the algorithm is an iterative one, the problem of finding is very easy. The problem of analysis is very easy. All we have to do is we have to assign the cost, we have to see how many times this is getting executed. Based on that, we can give the answer. But if the algorithm is having recursion, then we have to solve that in a different manner. So, that is the reason why we are trying to understand the basic relation, and based on these methods we can find the correct information related to the analysis of all these algorithms. So, we will have a small break, and after the break we will continue our discussion. Thank you very much. I welcome you back to the session actually. So, we were talking about how to analyze the algorithms, so especially with regard to the recursive algorithms. So, we were talking about the recurrence equations. So, let us start with one more example. Let us take this particular case T n equal to 7 into T n by 2 for n is greater than 1 and n is power of 2, and the initial condition T1 equal to 1. This is the recursive equation of a very famous algorithm called Strawson matrix multiplication algorithms. You know, the conventional matrix multiplication requires 3 loops actually. So, approximately it is order of n cube. So, that is the normal analysis of the matrix multiplication algorithm. The fastest matrix multiplication algorithm is Strawson, whose complexity is order of n power 2.81. Okay. So, let us go back to our problem solving. So, this is the recurrence equation of that particular thing. Now, we will try to see how to solve this by this particular method. We will try to compute the sequence. So, n is power of 2. So, I am starting with 2. So, T 2 equal to, see the equation, it is 7 into T n by 2. So, that means this becomes 7 into T 1, initial condition is 1. So, that means this becomes 7. So, repeating this logic, you can see T 4 equal to 7 into T 2, T 2 is 7, already we have computed. So, this becomes 7 into 7, 7 square. So, by increasing the values of n to 8 and 16, you can see very well we are getting some sequence like 7 power 1, 7 power 2, 7 power 3 and 7 power 4. See carefully the relationship between n and the sequence seems to be 7 power some factor. That factor, if you carefully analyze, for 2 we are getting a value of 1. So, for 4 we are getting a value of 2, that is nothing but the logarithm of n base 2. So, now you can see very well the whole behavior of this particular algorithm can be summarized as 7 power log n. So, this is what T of n, and you can see very well by analyzing this we can get lot of information. So, let us go to the proof part. Like I was telling you in the last session that by mathematical induction, if we could show that the condition is true with respect to n, and if we could able to prove that it is true for n plus 1 also, then inductively our hypothesis is right. So, that means if T n equal to 7 power log n, then by inductive means we have to prove that T of 2n equal to 7 power log of 2n. Why we are going for T of 2n? Because we have given in the problem itself that n is power of 2 actually. So, if you try to simplify this particular thing, so T of 2n equal to, see the original equation, it is 7 into T n by 2. So, that means T of 2n equal to 7 into T of 2n by 2. So, 7 into T n already we know is 7 power log n. So, that means this becomes 7 into 7 power log n. So, this can be simplified as 7 power 1 plus log n, and 1 I can rewrite as log 2 base 2. So, now you can see very well by logarithmic law it becomes 7 power log 2 n. So, that means now we can confirm that our assumptions is right. By the logarithmic reverse rule, you can see very well 7 power log becomes similar to n power log 7. So, you can see very well now this approximately becomes n power 2.81, that is the complexity analysis of Strawson matrix multiplications. So, the best advice I can give to you is that whenever you are supposed to analyze a recursive algorithm, you try to find the sequence and try to understand the relationship that exists among the sequence and try to find that. If it is an explicit one, then you are fortunate. Otherwise, you have to analyze the sequence to get the equation, and once you have the recurrence equation, then everything becomes very simple indeed. You can simply use your backward substitution or forward substitution to get the answers. Fine. Now, let us assume that we have such a equation, and let us try to categorize this into two categories for us. One is called the homogeneous equations and another is called the non-homogeneous equations. Homogeneous equation means RHS is going to be 0. If it is a non-homogeneous or inhomogeneous, then the RHS is not going to be 0. We can take a small example like this. You take the case of Fibonacci series. Already we have seen that the Fibonacci equation is T of n equal to T of n minus 1 plus T of n minus 2, because we have already seen that a term value is computed by adding the sum of the previous two terms actually, that is your f of n is equal to f of n minus 1 plus f of n minus 2. So, in terms of recurrence equation, this is nothing but T n equal to T n minus 1 plus T n minus 2. By bringing everything together, this becomes T n minus T n minus 1 minus T n minus 2 equal to 0. So, now you can see very well the RHS is going to be 0. If RHS equal to 0, then it is going to be known as the homogeneous equations. So, if we have an homogeneous equation, then we can solve it by using the conventional method like this. So, the form of a homogeneous equation is like this: A naught T 1 plus A 1 T n minus 1, it goes up to A k T n minus k equal to 0. This is a homogeneous equation because your RHS is going to be 0. Suppose if you are given an equation like this, means what you can do is you can convert this into a characteristic equations. So, the characteristic equation for this particular linear equation is A naught r power k. So, now you can see in the previous equation the last term of the equation is A k T n minus k. That k is what comes as the beginning of your characteristic equation. This is nothing but the order of the recurrence equations. So, now you have the characteristic equation and you have to solve these characteristic equations to get the roots actually. Suppose if you have a polynomial of degree k, then you will have k roots for that particular equation. So, based on this you can have the solution something like T n equal to C 1, first root is R 1. So, it is becoming R 1 power n plus second root C 2 R 2 power n, and it goes up to C k R k power n. So, here the C i's are constants and R are nothing but the roots actually. Two cases arises actually. In case 1, you will have the roots that are distinct in nature. The second case is you may have the multiplicity. For example, if I solve a particular equation, I may get roots something like 3 comma 3. So, that means the values are same, but I am having the multiplicity of 2. So, these are the two cases we will encounter. So, two theorems are available. So, we will see one by one. So, I will start with a numerical example itself, because the best way of understanding a thing is by means of the numerical means. So, let me take an equation which says T n minus 3 T n minus 1 minus 4 T n minus 2 equal to 0 for n greater than 1. Two initial conditions are given, T naught equal to 0, T 1 equal to 1. Imagine this is the recurrence equation of the a program that is given to you. Okay. Suppose if someone asks you to analyze the behavior of that program, so how you should start? So, you have to start solving the recurrence equation first, because that is what will tell us what sort of algorithm it is going to be. We can follow backward substitution method or forward substitution method, but in our case actually the equation seems to be slightly complicated, where those kind of things do not seem to work. So, we will try to attempt it using the traditional means. So, now you can see very well, I can write the characteristic equation for this. You can see very well, the last term of the equation is minus 4 T n minus 2. So, that means you can see very well the order is 2. So, we can bring that to the initial position. So, you can see very well the characteristic equation becomes something like r square minus 3 r minus 4, this is equal to 0. This is a homogeneous equation because RHS is 0. So, that is the reason why we are going for this characteristic equation, and we can see very well if you try to solve this using the equation minus b plus or minus root of b square minus by the traditional formula, you can see very well the roots of the equations are 4 and minus 1. Now, you can see very well, now you have two roots actually, one root is 4 and another root is minus 1. Two roots are distinct in nature, they are not same actually, they are distinct. So, we can go for the solution. Please recollect what we have seen in the previous slides. So, for every root there is one contribution to the solutions. Here you have two roots actually. So, that means your solution is having two terms actually. So, that means you can see very well it is going to be T n equal to C1, first root is 4. So, it is 4 power n plus C2, second root is minus 1. So, that means minus 1 power n. So, you can see very well T n equal to C1 4 power n plus C2 into minus 1 power n. Now, what is the value of C1 and C2? They are nothing but constants. Let us try to find the value of all the things. So, let us make n equal to 0. So, if we make n equal to 0, this becomes T0 equal to C1 4 power 0 plus C2 minus 1 power 0. The initial condition is already given as 0 for T0. So, your first equation becomes C1 plus C2 equal to 0. When I make n equal to 1, this becomes C1 into 4 power 1 plus C2 multiplied by minus 1 power 1. So, you can see very well this becomes 4 C1 minus C2 equal to 1. Now, I have two equations involving two variables. So, using the traditional methods you can solve and you can find C1 is going to be 1 by 5 and C2 equal to minus 1 by 5. I hope you know how to solve this, right. So, if you simply add these two things, actually you can see very well C2 is getting cancelled out. So, that means you will have 5 C1 equal to this thing, and you can see very well you are getting the answer as 1 by 5 and minus 1 by 5. So, you have to substitute this into your original equation. So, your original equation is T n equal to C 1 into 4 power n plus C 2 equal into minus 1 power, okay, right. So, C 1 C 2 already we have found it out. Now, you substitute this back into this equation. Now, you have the final equation like this. In other words, the polynomial of this particular algorithm is going to be like this. Like we have seen in the last review, if we know the exact symbol, we can substitute, we can assign that symbol to this particular thing. You can see very well, approximately this becomes a sort of exponential algorithm. Now, let us try to see one more example. I want to demonstrate that Fibonacci series is a difficult problem to solve. You may be surprised to know. I am saying it difficult because, say for example, if Fibonacci of 10,000, then Fibonacci of 10,000 will become Fibonacci of 10,000 minus 1 plus Fibonacci of 10,000 minus 2. If you keep on substituting, suddenly you will see you will have a very big tree which has got millions of nodes actually. And suddenly, even if a node involves a computation of a second actually, you can see very well the algorithm may take hours, and 10,000 is not the end number, we can put any number. So, that means if I put 1 million, 1 billion, fine, you have algorithm that runs even for many days, many months together. So, these are the algorithms that are creating lot of problems for software development, because you know very well the requirements of the modern industries is that the algorithm should take less execution time. So, that means our algorithm should be optimal, okay, fine. So, we will come back to our discussion. So, this is what the Fibonacci sequence is all about. T n minus T n minus 1 minus T n minus 2 equal to 0. So, the initial conditions are 0 and 1. So, I am going for the characteristic equation. Okay. So, you can see very well the last term in the equation is T n minus 2. So, that 2 will come here. So, this will become r square minus r minus 1 equal to 0. So, you know the equation, right. So, minus b plus r minus root of b square minus 4a divided by, okay. So, substitute back into that equation, you will get roots like this. So, 1 plus root 5 divided by, okay, what you see in your slide actually. So, you have two roots. You can see very well that these two roots are distinct. So, what should be the nature of the solution, that also you know already, it is going to be C 1 plus something and plus C 2 into something. This is what it is, right, fine. Just recollect the previous numerical examples. Now, we have an equation where two constants value we want, that is C 1 and C 2. So, let us try to substitute the value n equal to 0, you have your first equation. Then you make n equal to 1, you have the next equations. So, if you try to solve this, you can see very well the equations simplify to these two conditions, C 1 plus C 2 equal to 0. Then you have that 1 plus root 5 divided by something. So, to get, if you solve this, you get C 1 equal to 1 by root 5 and C 2 equal to minus 1 by root 5. You can substitute this back into the equation. So, your T of n becomes 1 plus root 5 odd something. So, now you can see very well your equation has got lot of terms and many are in terms of 2 power n, and I have told you already lots of exponential terms are involved. So, that means that the algorithm is a difficult thing to perform. That is, as n becomes very larger, find the complexity of the algorithm is also very high. Fine. Theorem number 2 talks about the second case actually. The first case we have seen that we will have roots and all the roots will be distinct, but in many equations we will get the similar roots actually. Say for example, I may get values something like 1 comma 2 comma 2 comma 2. So, here you can see very well the roots are not distinct. One root is 1, another root is 2 comma 2 comma 2 means same number, but having the multiplicity of 3. Suppose if this is the case, find the contribution of every root to the solution will be like this. So, it becomes the first contribution will be r power n. If the same root is coming again, the contribution is n into r power n. Please see very carefully. Next time if the same root is coming, it becomes n square into r power n. So, like that if the multiplicity goes on, it goes up to n power m minus 1 into r power n, where that m is nothing but the multiplicity. So, these are all the solutions of the recurrence equations. Let us see this particular example. You can see carefully, the recurrence equation is given like this: T n minus 7 T n minus 1 plus 15 n minus 2 T n minus 2 minus 9 T n minus 3 equal to 0 for this particular condition, n greater than something, T naught equal to 0, T 1 equal to 1, T 2 equal to 2. Now, you can see very well this 3 is the order that becomes something like r cube minus 7 r square plus 15 r minus 9 equal to 0. So, if you solve this using the traditional means, you will see you are getting the roots like r equal to 1 and you are getting root 3 and another 3. So, that means now no longer these things are distinct. In fact, we have a root 3 having multiplicity of 2, right. So, that means now you can apply this particular theorem. So, now you can see very well it becomes something like this. First root is 1. So, that means this becomes C 1 multiplied by 1 power n plus second root is 3. So, C 2 into 3 power n, again root 3 is coming. So, that means it becomes C 3 into n into 3 power n. Let us imagine if another root 3 is coming. So, what is your answer for this? That means, if another 3 comes, actually it becomes C 4 n square 3 power n. Suppose if another 3 is coming, so it becomes n cube 3 power n, like that it goes. Okay. Depending on the multiplicity, the root contribution will be there to the solution. So, now you can see very well, now we have multiplicity of only 2 actually. So, that means now our equation becomes something like T 1 equal to T n equal to C 1 into 1 power n plus something, right. Fine. So, now we have to find the constants C1, C2 and C3. So, let us try to substitute n equal to 0. So, if you substitute n equal to 0, now you have an equation C1 plus C2 equal to 0, substitute n equal to 1, substitute n equal to 2. So, you can see very well you are getting 3 equations having 3 unknowns. So, if you solve all the things, you will get the value C1 equal to minus 1, C2 equal to 1 and C3 equal to 1 by 3. So, substituting everything back into the equation, now you can see very well we are having a particular solution something like this. So, you can see very well after simplifying, now we are having the expression that captures the behavior of this particular algorithm. Again you can see very well it involves lots of powers of something. So, that means that this algorithm is also something like an exponential in nature. So, I hope now you would have understood how to solve the homogeneous recurrence equation, isn't it? So, all you have to do is you have to obtain the characteristic equation, you have to solve it and then you have to check whether the roots are distinct or not. If the roots are distinct, you have to apply theorem number 1. If the roots are having multiplicity, then you have to apply theorem number 2 and based on that you have to form the equation, you have to solve for unknowns. Finally, putting everything back into the thing, you will get the final answers. All the things are related to the homogeneous. In non-homogeneous conditions, your equation will be something like this. This is the general equation of your recurrence form, which is something goes like a naught T n plus a 1 T n minus 1, it goes up to a k T n minus k equal to f of n. So, the important difference between the homogeneous and non-homogeneous is that in homogeneous the right hand side is 0, but here it is not so, right. Fine. In some cases this will be the case. Under that particular circumstances, then this method should be applied. So, you can see how we are going to proceed. In the RHS, what we are trying to do is we are trying to rewrite f of n as b power n multiplied by p of n. So, here b is a constant and p of n is a polynomial in n. Let us take an example like this: T n minus T n minus 1 equal to n minus 1 for n is greater than 0 and the initial condition T0 equal to 0. So, we have to solve like this only. Assume that your RHS is 0. You just assume that RHS equal to 0. So, you will find the homogeneous equations, you take directly. Then you try to convert your RHS into a form b into p power n, right. So, you will get roots from both homogeneous category as well as the non-homogeneous category. Now, you try to combine, then you check whether the roots are distinct or not. If the roots are distinct, fine, you can go back to your theorem number 1 and you can apply. Suppose if you feel that the roots are not distinct, involve certain multiplicity, then the theorem 2 should be applied and you have to form the solution. So, now you can see the equation T n equal to T n minus 1 equal to 0. So, that means this becomes r power 1 minus 1 equal to 0. So, that means I am having one root, that is 1, fine. Now, I am going to the RHS part. RHS part is n minus 1. So, I am trying to rewrite this to suit my case. So, I am saying it is 1 power n multiplied by n minus 1, I am saying as n power 1 minus 1. Here you can see very well, b is going to be 1 and d is going to be 1. So, if this is the case, the theorem says it is going to be, the solution is going to be r minus 1 power 1 plus 1, because your d is 1. So, it is d plus 1, that is you will have 1 plus 1. So, that means you will have roots 1 and then 1 again. Already you had the value of 1. So, that means now you have 3 roots actually. So, that means it is not distinct, it is having the multiplicity of 3. So, that means theorem 2 is applicable. So, you can see very well it becomes root 1 with the multiplicity of 3. So, please remember the theorem, every term contributes something to the general solution. So, the contribution of 3 ones are like C1 into 1 power n plus C2. Now, you can see very carefully it is n into 1 power n. The next thing is C3 n square 1 power n. So, if you try to simplify everything, it becomes C1 plus C2, like that it goes. So, now we have to find the values of C1, C2 and C3. You know very well, for solving 3 unknowns actually you require 3 equations, and in your problem actually only one initial condition is given, that is t0 equal to 0. So, but it does not stop us to find the remaining things. All we have to do is make n equal to 1 and try to find the initial conditions. So, you have the original equation. So, if you make n equal to 1 by substituting in the original equation, you can see very well it is going to be 0, and by substituting n equal to 2 you can find the initial condition as 1. So, now all I have to do is I have to go back to the solution, I have to make substitution like n equal to 0, n equal to 1 and then n equal to 2. So, now I will have 3 equations having 3 unknowns, and you know how to solve these 3 equations involving 3 things, 3 constants, and if you try to solve this, you will have the final value as n into n minus 1 by 2, and you can see very well we can approximate this something as n square plus something, and as I said earlier, the largest degree play a very important role in the solution. So, that means now I can say that this algorithm is something like order of n square. So, let me recollect everything. So, first you start with the assumption that RHS equal to 0, gather the roots, then try to rewrite your RHS and try to get the roots, combine everything, then apply the theorem 1 and 2. This is the third method called Master's theorem. So, Master's theorem is a theorem which is applicable, which comes very handy for finding the analysis of certain algorithms. Normally, the algorithms involve strategies like divide and conquer, then Master's theorem comes very handy. So, this is the Master's theorem, f of n equal to a into f of n by b plus c into n power d, and whenever you see the recurrence equation of an algorithm fits into this particular template, then straight away you can write the answer by using this particular theorem. So, whenever you see that your A is less than b power d, then you can see the answer is going to be order of n power d. Suppose if you see A equal to b power d, then the answer is going to be order of n power d log n. Similarly, if A is going to be greater than b power d, then the answer is going to be big O of n power log A, right. So, let us try to see some examples. So, one example I have taken where T of n is equal to T 2 into T of n by 2 plus x n. So, you can see very well that template is being fulfilled. So, if that is the case, then I can apply the Master's theorem. These are some of the examples. F of n equal to 2 into f of n by 2 plus x into n square. F of n is nothing but your T of n only, right. So, that means this is nothing but something like T n equal to 2 into T n by 2 plus x n power 2. Okay. So, suppose if any problem is given like this, you do not have to solve it using the conventional method. Straight away you can see this fits into the template. If the template is available, then you can see very well, you can get the values of A, D, B, etc., and you can check whether A is less than b power d. You can see very well in this particular case, you can see that condition holds, that is 2 is less than 2 power 2. So, that means